Welcome to this explainer. Today we're going to calmly unpack a really fascinating paradox in modern artificial intelligence. We have these systems that can perfectly name and categorize objects, yet they routinely fail when they actually have to act within physical spaces. We're going to view this problem through the lens of a rigorous framework known as the energetic paradigm. Our goal here isn't to hype up some revolutionary new model, but rather to understand a serious, academically grounded framework for measuring true spatial AI. Let's jump right in.
So here's our roadmap for today. We'll cover the recognition gap, the hierarchy of spatial sufficiency, and the energetic paradigm. Then we'll follow the causal chain, examine a theorem-aligned benchmark, and finally, redefine our evaluation standards.
Section 1. The recognition gap. Correct labels do not equal reliable action.
Modern multimodal AI systems are just incredible at assigning correct category labels to what they see. But despite this high recognition accuracy, they remain completely unreliable when they have to act in spatially grounded physical environments. It's a fundamental disconnect. Recognizing what an object is creates this false assumption of intelligence. A label doesn't tell you where the object is, what's supporting it, what might be blocking it, which paths are safe, or how those relations are going to change once you actually take an action. Instead, true action requires a causal sequence. It starts with structural coverage, leads to the recovery of the hidden state, and that is what finally enables reliable action.
Section 2. The sufficiency hierarchy. Different information requirements. To really academically ground this distinction, the paper draws a strict line between different levels of what they call sufficiency. And it's absolutely crucial to emphasize that these are fundamentally different information requirements. We're not just talking about different levels of model accuracy here. First up is recognition sufficiency. This is simply the ability to assign a correct category label to an observation. The paper formally proves this is strictly weaker than spatial competence. Why? Well, because a representation might preserve enough information to accurately identify an object while totally discarding the hidden geometry, the obstacle relationships, and the free space conditions you actually need to physically move around it.
Moving up the hierarchy, we hit spatial state sufficiency. Now, this is where true spatial intelligence begins. It requires the system to acquire, preserve, and organize hidden physical realities, things like support, containment, and occlusion. It's really about recovering the latent state necessary to move reliably under physical constraints. And from there, systems also have to achieve relation sufficiency to understand exactly how these objects interact, and dynamic sufficiency to predict how those relations will shift over time.
At the very top, we have long horizon sufficiency. In a real-world deployment, an estimated spatial state is reused over and over through a sequence of many actions. So this metric evaluates whether the system can maintain transition stability across time without a catastrophic failure. Essentially, can it minimize accumulated regret over a long horizon? That's the ultimate test of an embodied system.
Section 3. The energetic paradigm, a framework for measuring spatial competence.
The energetic paradigm, or EP for short, is this rigorous theoretical framework used to evaluate whether a system actually has the structure necessary to act reliably rather than just name things. It gives us several formal interpretations. First, structural coverage dictates what can be recovered. Second, as we just mentioned, recognition can actively discard action-relevant structure. Third, grabbing multiple views isn't just about getting more data. It fundamentally changes the recoverable state by exposing hidden variables and reducing uncertainty. Fourth, failing over a long horizon is really just small structural errors accumulating over time. And fifth, building complex dynamics models to predict the future is entirely secondary. A sophisticated world model just cannot compensate for information that was never observed or structurally represented in the first place.
The core idea here is summed up perfectly in this quote. Within EP, a dataset is not just a huge pile of samples, it's a structural operator. If your dataset lacks structural coverage, meaning it's missing views, relations, or transition states, it creates an irreducible ambiguity floor. And here's the kicker. You cannot solve this ambiguity just by pumping up the parameter size of your model. Scale alone literally cannot fix a lack of structural observability.
Section 4. The causal chain. The exact progression of spatial competence.
If we actually want to build reliable spatial AI, evaluation has to follow this exact causal sequence dictated by the paradigm. It starts with structural coverage in the data. That coverage enables an accurate state posterior. A good state estimation then allows for relation recovery. That leads to transition stability when actions are taken, which finally results in minimizing long horizon regret.
You just can't skip steps here. And if you do ignore this chain, you hit a fundamental wall. A representation that prioritizes recognition alone basically compresses the system around the wrong energetic requirement. It learns the category, sure, but it discards the exact variables needed for action. True spatial intelligence requires a representation that preserves relations, free space conditions, and the actual consequences of transitions.
This really highlights why evaluation absolutely must follow the causal chain. A tiny state estimation error might look totally harmless in one isolated observation, but in robotics, that state gets reused. Those tiny errors propagate themselves through the transition system, compounding with every single sequential action, and rapidly accumulate into long-horizon regret or total failure. It's like a domino effect.
Section 5. A theorem-aligned benchmark. Testing S3WM under structural coverage. To actually verify these theoretical mechanisms, the authors didn't just write out equations. They instantiated a concrete model called the Structural State Sufficient World Model, or S3WM, inside a highly controlled synthetic benchmark. And pay close attention to this setup. It artificially locks recognition accuracy at a perfect 100% across all the tested regimes. By making recognition trivially perfect, the benchmark isolates the causal mechanism. It ensures that any variation in performance strictly comes from the system's ability to recover the hidden spatial state.
Now, take a look at the data shift here from the low to high coverage regimes, as the structural coverage index, or SCI, goes from 0.43 up to 0.96, the state error, the RMSE, just plummets. And look at that final column. Horizon success jumps dramatically from a coin flip 57.3% all the way up to 95.6%. Yet the recognition accuracy never changed. It was locked at 100% the whole time. This mathematically and empirically proves that recognition is simply not spatial sufficiency.
We do need to interpret this conservatively, though, exactly as the authors intend. S3WM is presented as one theorem-aligned instantiation to prove a mechanism. Its multi-view fusion, state estimation, and dynamics modeling correspond to different terms in the framework. But it is not being presented as a universally superior final production architecture for real-world robotics. The benchmark is evidence for the formal mechanism, not a replacement for testing on physical embodied systems.
Section 6. Redefining evaluation. Reporting the full causal chain. Because we've clearly seen that recognition accuracy can completely mask long-horizon failure, we really can't rely on single-step image labeling metrics to judge embodied systems. The takeaway is clear. Spatial AI benchmarks must separate these distinct measurements. Recognition accuracy should definitely remain part of the evaluation. It's still useful, but it must not substitute for the rest. We have to actively measure state root mean square error, relation F1 scores, uncertainty, transition error, long-horizon regret, and ultimately, sequential success rate. This leaves us with a final provocative thought about the frontier of AI, and a question we should be asking of every new spatial model. If a system correctly recognizes every visible object in a room, does it actually possess the intelligence to act upon them safely and reliably? The answer, as we've seen today, is no. A system that can name the world does not necessarily possess the state required to act reliably within it. The energetic paradigm makes this distinction measurable by proving that naming the world is just one narrow projection. True spatial intelligence relies on structural availability, accurate state recovery, constraint-sensitive transitions, and stability across time. Keep these metrics in mind the next time you evaluate a spatial AI system. Thanks for joining me on this explainer, and keep learning.